Okay, this lesson is on derivatives of exponential and logarithm functions. So this is the last of our tools, the last of the formulas that we're going to use to help us find derivatives of any function, right? So here are formulas for e to the x, a to the x. See, these are exponential functions. We have natural log of x and log base a of x. Now, honestly, personally, what I usually do in order to memorize these, I actually only memorize e to the x and natural log of x. For two reasons. Number one, they're the easiest to memorize because the derivative of e to the x is e to the x. Then, of course, whatever is in the x up there, you have chain rule, you got to take the derivative of that out. But as you can see in the formula, it's e to the u, so e to the x, times du dx, so that's the derivative of the exponent. Natural log of x is just 1 over x, so 1 over whatever the argument is of your natural log. And then again, chain rule, whatever the thing inside the expression inside the natural log, it has a derivative, then you got to take that outside and multiply it. Okay, you could actually change any of the other two, the a to the x and log base a of x, into a natural log function, and then it can be done using those two formulas. So I will show you in a minute, but of course, if you want to memorize, it's not a bad thing. This is the formula you would memorize for a to the x power, and this is the formula for for the log base a of x. So the beauty of memorization is that you can get what you want really quickly, whereas I don't memorize it. So if I rely on natural log to help me manipulate any of these functions, there's a little bit more work for me, but less memorization. So again, your choice. More memorization, less work. Less memorization, more work. Up to you, okay? All right, so first problem asks us to find the derivative. It says find the dy dx of this function y equals e to the negative x over 4, right? So you might want to rewrite this so it's a little bit more familiar, because a lot of times students get really caught up with this x over 4. So if you really want to, this is e to the negative 1/4 times x, right? So you got to be comfortable in seeing that negative x over 4 is the same as negative 1/4 x, because then when we take the derivative y prime, when we have e to negative x over 4, remember, anytime we take the derivative of e to whatever, it's still the function itself. So we still have this e to negative x over 4. Then you got to do chain rule. Chain rule says, okay, what is the derivative of this thing on top? What is derivative of this on top? Then you got to be able to see the fact that, oh, really? That's a coefficient of negative 1/4. That's your derivative. So negative 1/4 will be coming out this way. So then, if you were to write this out nicely and completely, this would be negative 1 over 4 e to the x over 4, because that negative x over 4 brings it downstairs. And this will be your final answer. Okay? And that's it for e to the x. E to the x really has that really interesting thing of it being itself, the derivative of itself being itself. All right? I think we talked about this a little ways back in our homework, I think. Anyway, okay, so number 2 here, you have now 2 product rules. How do you know you have product rules? Because you have x times x and x times x. So here is your product, the first product, x squared times e to the x, and you have this x times e to the x. Okay, all right, so product rule says take the derivative of the first one, which gives me 2x, and again, I'm going to color code for you, so then we keep the original e to the x, okay, plus, now you keep the original x squared, and believe it or not, this is the derivative of e to the x, so that's why it's in blue, it's e to the x. Okay, minus. Okay, typically, again, I don't put my minus in my product rule because I find it to be a little bit more annoying and it's kind of in the way, so I like to put it outside and deal with it later. Okay, I'm going to take the derivative of this x, which is 1, and you keep your original e to the x, and then again, you keep the original x, and then the derivative of e to the x is e to the x. Okay, now clean up. You have 2x e to the x plus x squared e to the x minus e to the x minus x e to the x. Right. There is something you can combine. You have 2x e to the x and minus x e to the x. So you would have x squared e to the x plus a single x e to the x minus e to the x. What they all have in common? E to the x. So let's factor that out. Remember, we want it as factored as possible. There's a good reason for this in chapter 5 in the future. Okay, and that is your y prime. E to the x times x squared plus x minus 1. you want the second term to be in standard form, and that's why I moved the x and the x squared around a little bit so that I can have my second factor in standard form. Okay. All right. Okay, so number 3, we have y equals x to the 1 minus e power. So you have to really distinguish the difference between these two type of problems, where you have x to a number versus a number to the x power. So what a lot of students get confused with is e is actually a number. E is like pi. It is a number that occurs naturally. So it is not a variable. So in this case, in this particular problem, we actually have this situation here. When we have this situation, we simply use power rule, right? So power rule says drop your power and then subtract 1. So y prime here is now 1 minus e x. Okay, so then the exponent was 1 minus e minus 1 now because we took the derivative. So we have negative e. That's the only thing left. Okay, clean this up. 1 minus e over x to the e power. And that is your derivative. Okay, when it is a number, a number base to a variable exponent, then we got to use the formula we have up top in this lesson. Okay, all right, so that's actually the next one here. We have y equals 3 to the cotangent x. See how my variable is in my exponent? So my number is a base. My base is a number here, so we can use the formula. Okay, so I'm going to show you how to use the formula first, and I'm going to show you what I would do without the formula because I don't typically memorize the formula. So formula up here says it's a to the u, natural log of a, du over dx. Okay, so that means that the formula says a to the u, choose really short term memory, a to the u, natural log of a, and then u prime. Du dx is u prime, meaning the derivative of u. Okay, so what is a? A is your base. So the derivative of this, y prime, is equal to, okay, so a to the u, that means you actually write this whole thing again. So 3 to the cotangent x, because u is my exponent, natural log of your base, 3. Then u prime says, okay, what is the derivative of this cotangent? It is negative cosecant squared x. And that is your final answer. Very, very unclean, but that is your final answer. I probably would just clean up a little bit and say, all right, negative natural log of 3, that's a coefficient, right? And cosecant square x, and then times 3 to the cotangent x, just so it's a little bit cleaner. Okay, all right. So how would I do it without memorizing this? Because I don't like memorizing these formulas. Is there a way to approach this without memorization? So you then need to use everything you've learned so far. You would then need to use implicit differentiation to kind of help you see how to work this out. The biggest problem we have here is that the variable is in the exponent. So how do we bring that down? Well, you have a tool. You have a tool from trig, even algebra 2. You have log or natural log. And again, I choose natural log because I know the formula for natural log is a lot easier. It's 1 over x, right? So what do? I have my original problem here of y equals 3 cotangent x. I know that natural log, once I apply to both sides, first of all, that's okay because natural log as long as I do it to both sides, it's balanced. Secondly, natural log will allow me to bring down the cotangent x as a coefficient. So now it becomes natural log of y equals cotangent x times natural log of 3. Ooh, that looks a little bit more doable now, right? Okay, so then I will just, I will try to move this around a little bit because I will try to remind you a natural log of 3 is a coefficient, it's a number, right? So the only thing I really need to work with is this cotangent x on the right-hand side. Okay, now how do I take the derivative? Well, implicit differentiation says you need to make sure that y has a y prime, right? Because now y is not alone, you have this natural log, but it's not too bad. So natural log of anything, the derivative is 1 over that anything. And since that's a y, we need to tap on a y prime because this is implicit. Okay, then equals, next door you have this natural log of 3 because that is your coefficient. Okay, what is the derivative of cotangent? Negative cosecant square x. And so again, I want y prime by itself. And don't forget, you don't want this 1 over y, so you multiply y on both sides. So this is nice and clean on the left-hand side. You have natural log of 3 times negative cosecant square x. Hey, what was y? I don't want y here. Well, y, looking at my original problem, y is equal to 3 cotangent x. So I'm going to multiply that by 3 to the cotangent x. And guess what? I have the exact same thing as next door, right? So again, using the formula you memorize, but you notice I only took 2 steps to get there. I did not memorize the formula, then it took me 1, 2, 3, 4, 5 steps to get there. So I will get there. It's just depending on what you are more comfortable with in terms of memorization. Okay? All right. Ooh. Next problem, we're on natural log. All right, so natural log of 2x plus 2. All right, so when you are taking the derivative of this, don't forget you have a chain rule inside. So the outer layer is natural log, the inside layer is 2x plus 2. What is your derivative? Well, y prime, let's deal with the outer layer. Natural log gives me, or the derivative of natural log is 1 over this argument of 2x plus 2 that's inside. Now, then when you're done with that piece, the inside piece gives me a derivative of 2. Okay, let's clean up. We have 2 on the top, factor out 2 on the bottom, so that you can reduce out the coefficients and leave yourself with a nice clean answer, 1 over x plus 1. That is your derivative of this awesome natural log function. Okay. All right. Same thing here. Don't forget there's actually a product here. This is x times natural log of x minus x. So you got to make sure you, again, take a minute here to realize you have product rule here. Okay. All right. So y prime equals, I'm going to take the derivative of the first term, which is x, and that's 1, times the original form of natural log of x. Beautiful. Okay, plus, okay, you now keep the original x, and then the derivative of natural log of x next door here is 1 over x, and don't forget minus, what is derivative of x here? Minus 1. Okay, all right, clean up. You get natural log of x plus, what's x over x? 1 minus 1. So this one you only have a nice little natural log of x. So a little bit different than what we learned a couple days ago about the inverse trig functions. The inverse trig functions actually give us really, really gross answers in terms of, like, you know, bigger expressions, bigger values. But for each of the x and natural log of x, it actually gives us like smaller terms, right? For a to the x and log base a of x, then it gets more complicated because, you know, they have bases in different ways and their formula is a little bit more complicated. Okay. All right, so now I have this log base 2 of root x plus 1. Again, I will do the same thing as before. I'm going to show you how to use the formula first, and I'm going to show you how I usually do it. So go back up. I am going to go ahead and look at my natural log here. So it says natural log is 1 over u natural log of a. Okay, so 1 over u natural log of a, and then u prime. Okay, all right. U is what's in the log, so this is the u piece. Okay, all right, so let's see. Y prime equals, the formula says 1 over, u is the root x plus 1, so root x plus 1. Natural log of a, what is a? A is your base, just like before. A is your base, 2. Okay. And then u prime. Now this thing itself, this root x plus 1 has a derivative on its own. So don't forget to change the root now to a 1/2 power. Bring down the 1/2. X plus 1 now to negative 1/2. Okay. All right. Now let's clean up. This is the calculus portion over. Now let's do cleanup. You have 1 over natural log of 2 root x plus 1 times 1 over 2 root x plus 1. That's multiplication. So then it's really nice because now you have 1 over 2 natural log of 2 x plus 1. And that will be your final answer. Okay. All right, how would you do it without the formula? It's doable, just again, a little bit more work. Now, recall back in trig and algebra 2, you can change any log of any base with a change of base formula. So any log base can be changed into log 10 of something over log 10 of something, or you can change to natural log over natural log. Of course, I want to use natural log because if I change in log base 10, it doesn't make any sense. It's just back to the same problem. So this log base 2 of root x plus 1, I can change that so that my equation is now y equal to natural log of root x plus 1 all over natural log of 2. Right, that's the change of base. I can change it to any log base of the big term over any log base of the base. Right, so I change the natural log of the big term, x root x plus 1, and I change it to a natural log of the base 2. Okay, so now I gotta remind myself, this is really a coefficient. Natural log of 2 is a number, right? So it's not a variable, it's just a number. And then I have this natural log of root x plus 1. Okay, so when I take the derivative, this coefficient still stays. It's 1 over natural log of 2. Then I only have this little chain rule to deal with. So the outside layer is natural log. It becomes 1 over root x plus 1. Then the inside layer has a derivative of its own. So the root x plus 1 now becomes 1/2 x plus 1 to the negative 1/2. Okay, so clean up. Natural log of 2, x plus 1, 1 over 2, root x plus 1. So I get 1 over 2, natural log of 2, x plus 1. Same exact answer as before. And this time, I don't think I have as many steps. I think I can 1, 2, 3, 4, 5 steps again, but using the formula still gave me 3 steps. So I'm not too far away from not memorizing or memorization, right? So again, up to you. Whatever you're more comfortable with, memorization or not memorization. And then the problem like the next one, maybe memorization is the way to go, okay? So next problem number 8, you have really, this is a quotient, right? It is a quotient because at the top you have a variable, it's x. So x times, oops, excuse me. I don't know what happened. Give me a minute. Okay, good. My iPad was doing something weird. Okay, so you have x over, and then log base 5 of x, right? All right, so remember, we got to use quotient rule. So y prime, low d high minus high d low. So low is still the log base 5 of x. D high, the derivative top is 1, minus high, the top is x. D low, okay, D low, this gets a little bit tricky, right? So the derivative bottom is 1 over u is your variable, so it's your x, it's your argument. Natural log of 5. And then the x itself, what's the derivative of that? It's 1, so I don't have to worry about du dx, okay? All right, and then all over, don't forget all over, low squared, right? Okay, all right, so let's clean up. That's it. That's the hard part of the calculus, right? So log base 5 of x minus, well, this x here and this x here will reduce out, leaving with just 1 over natural log of 5 all over log base 5 of x, the whole thing squared. Okay, now remember our golden rule. So this is the only thing where I'm like, yeah, our golden rule of one fraction still applies here. This is really gross. So you really want to make sure you clean it up. And by cleaning it up, I think we're making it even grosser, but it will turn into one fraction. So again, the trick is the same as before in implicit differentiation. You look at the small fraction up top, the denominator is natural log of 5. You want to multiply everybody by natural log of 5. So that way I can have clean fractions. So make sure you distribute to everybody. Okay? All right, so that will give me natural log of 5, log base 5 of x, minus 1 all over natural log of 5, log base 5 of x squared. Okay, and that's it. That is pretty gross, but that is your final answer. Just make sure where you're writing your bases versus your actual argument of your logs, you make that really clear what's the base and what's the argument. A lot of times some of you write really messy, and so it's really hard to tell what's your base and what's your argument, so make sure that it looks right. So what I'm trying to say is make sure it looks like log base 5 of x, not log of 5x. They're all the same size. That's gonna be what I'm interpreting. Okay, all right, that's it, guys.